Greetings, as the Organians from the original Star Trek episodes would say. Welcome, welcome. Our village is yours, Mr. Spock. So, I'm starting a new series here that I'm calling the Tau of Capacitors. And I originally thought, well, maybe I'll try and do it all in one. And, it could end up being like 8 hours or something. So this will be a multi-part series, and I don't know whether it will be like one video or 2 videos or 20 videos. We'll see as we go along. There's not going to be a lot of discussion. I'm sorry. There can be as much discussion as we like. There's not going to be a lot or any experimentation. It's just going to be looking at capacitors from a didactic sense, just getting a feel for how they work, the theory behind them, etc. And so I'll be sharing my vast knowledge or ignorance on the topic, as I'm not an electrical engineer. I'm coming at this from the outside. So, quite honestly, I'll be learning as I go along as well. And potentially others might learn a little bit too as we go along with capacitors. And as we're talking about different things, in the back of my mind, there are also certain findings just about how capacitors behave that we can riff off of and think of, that would be a neat experiment to try to set up to look at that aspect or this aspect. But the series is entitled the Tau, T-A-U, of Capacitors. And there's a very clever, a silly kind of play on words there, that the Tau is a reference to the Tau time, T-A-U, which is in relation to the curve for how a capacitor charges and discharges. There's a specific curve, just like there's a Tau time for an inductor for how the magnetic field charges. You may all also heard it called the RC constant. So that's why it's called the Tau time. But then there's also the Eastern idea of Tau, T-A-O, and that means the way of the universe, or the way of something. I have no idea what it means. But in a Zen way, that means I understand it perfectly. So that's why it's called Tau. There's also, there's potentially even a third, just to whet your appetite. This will probably be like part 15 or something. But I've been rereading a book on phi, which is the golden ratio number. Irrational. Getting back to Zen, it's irrational. Just like a circle and the diameter, you can't express it in numbers. But I don't think that they chose Tau because the first Tau time is the golden ratio, but it's darn close. The inverse of the golden ratio. It's darn close. I think it has more to do with Euler's number. I don't have a book on that that I'm reading. But Euler is also an irrational number. Let me stop babbling. Let's just talk capacitors. And we'll do a lot of that, and hopefully I'll break it up into lots of installments and do them more frequently. So away we go. So if we're going to talk about capacitors, it's probably best to begin at the beginning. And here's Science Direct. A capacitor is an electric component or device that stores energy by accumulating electric charges on opposite surfaces, which are separated by an insulating layer. So that's the basic idea, but there's, right off the bat, a wrinkle here. The insulating layer, because there are two properties of importance for the capacitor, and one is how well the insulating layer prevents the passage of electricity, and the other is something called the dielectric constant of the layer, or the relative permittivity of the layer. And so if we scan down here, let's see if there's a good little snippet. well, here they at least mention the insulator or dielectric. And going back for a minute, the plates can be aluminum foil, or they could be copper, or they could be other materials. You just want to have something that's conductive, because you're going to want to draw the charge off. And then the insulator can be air or ceramic or paper, or we're going to talk about that more in a moment. So Wikipedia actually has a good illustration here. So you have your negative charge here, your positive charge, your electric field, and then here is your insulator, which is also dielectric. And because it's a dielectric, the charges orient themselves like that, with the negative going there to a positive, negative to a positive, lining up against the negative. How easily these charges here flip in response to the electric field is the relative permittivity, and we will talk a little bit about that. So here we just have this snippet that dielectrics have high electrical resistance. A good dielectric is therefore a good insulator, but if you're doing the Venn diagram sort of thing, the reverse is by no means true, that a good insulator is necessarily a good dielectric. And while we're at it, we have this nice little simple diagram of the dielectric constant, I guess that's kappa, is the relative permittivity of the substance over the permittivity of a vacuum. And so the name for that dielectric came from this gentleman, by a request from this gentleman. And so much always seems to go back to Faraday, doesn't it? And it's dia, which that's a Greek term meaning, I think, across. I looked at it before, something like across or through. So like a cross electric, because you have the two plates and then you have this material that the electric field is going across. Let's spend a little more time on this just because it is important. So relative permittivity, I guess they're trying to get rid of dielectric constant. I like dielectric constant. And as we just said, it's the ratio of the electric of the permittivity compared to that in a vacuum. So the vacuum, it's 1 by definition. Air is essentially 1, and here's the first one. Teflon is 2.1. So why am I harping on that? That means that if you had an air capacitor with air between the two plates, and then you replace the air with Teflon, the capacitance of your capacitor would increase approximately 2.1 fold. If it was from vacuum to Teflon, it would be exactly 2.1 fold increase in capacitance. So the dielectric plays into the capacitance of your capacitor, and you can also see, because it affects the capacitance, that the energy in the capacitor is being set up by the charges on the plates, but since the capacity can vary, the energy is really stored in the dielectric. So it's, sometimes you hear that, and so now you know why. And you can see that there is a tremendous variability in the different materials. Here's mica, and we'll talk a little bit more about some of these materials, all the way out to things like barium titanate, which has a 1,200 to 10,000 fold greater relative permittivity or dielectric constant than air. Lastly, on this part of the discussion, because things can never be simple, the dielectric constant or relative permittivity is also frequency dependent. So they're giving it here for low frequency, or they talk about the relative static permittivity, which can be measured. And I think that's what we have here in this chart of permittivities, is the static permittivity. As you increase your frequency, and this is something I didn't know until I started this little discussion. from our AI overview. The relative permittivity decreases as the frequency of the applied electric field increases. Now, what that also means is because the relative permittivity is decreasing, that means the capacitance of your capacitor is decreasing at higher frequencies, and I did not know that. So here's just a little chart that I found. This is the prediction of the change in dielectric constant based from frequency for these different materials. And so here's about 100 hertz. About the fastest I'd ever be going is 100K, and really with solid state relays maybe about 20K. And so we can kind of see there is a noticeable decrease, maybe like 20% with that one. And this one's got a lot of decrease. Some of them don't seem to change too much at all. So that was fun. So now we've got a good idea of what a capacitor is, and also why, of course, there are consumer items made as capacitors, but this capacitance is all over the place. Whenever you have two conducting materials with differing charges that are separated by an insulating material, that the insulating material can polarize, and even air to a slight extent will polarize in relation to the two separate charges, then you have capacitance. So that's why they say there's no such thing as like an ideal inductor or an ideal capacitor. There's always capacitance and inductance with all components. And not to go down this rabbit hole entirely, but just to mention very quickly, here's a nice picture of the phospholipid bilayer, such as you would have in a human cell, or it doesn't have to be human. And it's got a couple things. It's got a hydrophilic head, meaning it loves water, and a hydrophobic tail, meaning it fears water. And so it spontaneously arranges to have the two sides that don't like water on the interior and the sides there on the exterior. And so now you can have two spaces, the space outside of the cell, extracellular, and the space inside of the cell. And you find that cells do a lot of work pumping ions from the intracellular to the extracellular and from the outside to the inside in order to maintain an electrical gradient from this side and this side. So in a sense that starts to sound an awful lot like a capacitor. If we, again, I'm not going to spend too much time on this, but here we see a recent article that was 2013, the measurement of the dielectric constant of lipid bilayers. And so there is a dielectric constant with the lipid bilayer, and it has a electric gradient across the lipid bilayer, and then sometimes that discharges, and you get things like muscle contraction and thoughts and things like that. So let's not get too deep. Let's go back to capacitors like you might buy off the shelf now. Even before then, just to mention really briefly a little bit about the history. So it goes back to here, and I think the most popularized idea is the Leyden jar. And one of the goals I have for a project is to try to 3D print a variable capacitance Leyden jar. So perhaps if I get around to that, we can discuss this history more. But let's get back to sort of more practical things, and here we can look at a picture of a bunch of different capacitors. I'm not sure what they all are. This looks to be an electrolytic capacitor. This looks to be a ceramic capacitor. This is maybe a film capacitor. There's mica capacitors as well. And these are two interesting ones. These are variable capacitors. They look like with air as the dielectric and those are also known as trimmers, and so you can adjust things with this knob in order to adjust the capacitance manually of the capacitor. So just a couple points real quick. This is kind of the big daddy here, this blue one, and that's maybe the size of your thumb, probably a little bit smaller, and it's 4,000. It has a capacitance of 4,700 microfarads, and we're going to get into all that in a moment, and it can go up to 35 volts. And so the two plates, I believe, are jelly rolled inside of this, and it often has water as part of the dielectric material. But the point I want to get to, and we could actually put this in a spreadsheet and determine it entirely, but we need to talk about more about capacitors before we do that, is the charge or energy stored in this capacitor. I'm just saying off the top of my head, if you had like a 1.5 volt battery that was this same size, it would probably be about 1/1000th maybe the amount of charge stored, and that's because the battery is storing the charge chemically, and this is storing it, as we mentioned, in the dielectric. So we've headed out to DigiKey now, and I just typed capacitor in there. These are the top results. So they have nearly 1 million ceramic capacitors and over 100,000 film capacitors. And now recall the discussion of the different relative permeabilities of the different materials that could be the dielectric. So here's some tantalum capacitors. I just like the name. Mica capacitors, PTFE. Here are your variable capacitors. Here are your aluminum electrolytics. And here's one we didn't talk about, a double layer, also called a supercapacitor, which stores more charge than a regular capacitor, but still nowhere near a battery. So rather than me doing like some 3-hour Fidel Castro lecture on capacitors, let's wrap up part 1 here. And I'll just tell you what we're going to talk about in part 2. And that'll be getting down to some more practical stuff rather than just the theory of what a capacitor is and how it works. But we know that one of the things that determines the capacitance of a capacitor is the dielectric constant. But what are the other parameters that determine your capacitance? And I mean, I'll just tell you now, we'll talk about it more, but it's plate area and how closely, how thin the dielectric is. We'll also talk about something called equivalent series resistance, which I think it's basically just the internal resistance of the cap. And that idea comes very much into play if you're trying to have a high Q factor LC tank circuit. So for instance, aluminum capacitors have a lot of water. They may have equivalent series resistance, ESR, of I don't know, like 20 ohms or something, whereas ceramic, it might be 0.1 ohms, and the same with film. But let's wrap it up here, and if I got anything wrong, just understand I'm not an electrical engineer. I'm coming at this as an outsider, but I'm having a lot of fun with it and learning a lot myself. If you're having fun with the channel as well, remember to hit the like and subscribe buttons. And if you want to support the channel, there's a couple write-ups that I have linked in the video description on health topics that you can pick up as an ebook or an electronic ebook off of Amazon for like a couple bucks or something like that. In any event, thanks for coming along, stay healthy, and we'll get part 2 out soon. Bye-bye. Okay, very last thing, bonus material. I realized I never said anything about Tau, and I'm entitling this the Tau of Capacitors. And when I was reviewing it and the start of this, looking for interesting snippets off of Science Direct, the voltage in the capacitor, however, needs a certain time to equalize with DC voltage source. This is described by the constant Tau. tau is defined as the time that the capacitor needs to reach 67%, which is an interesting value of the voltage level of the DC voltage source. So that'll be part 3. We'll actually get around to talking about tau and the charge and discharge curves of a capacitor, because there's a lot of interesting stuff there too. Okay, carry on. Sorry for the interruption. Stay healthy. Thanks for coming along. Bye.